Okay, we're here to talk about inverters today. I have a short period of time, and it's a pretty big topic. Have any of you, maybe you can just give me some feedback right now. Inverters kind of come in two major categories at this point. There are inverters that work with batteries, and there's inverters that work without batteries. Anybody have any idea what I'm talking about, or what your priority would be today? We have limited time, and so it's hard to cover everything. So
DC to AC.
That's inverters. They all do that.
You got three-phase, single-phase too.
I'm not going to go too much into that. Mostly single-phase. But battery-based versus non-battery-based.
Grid tie.
Grid tie. Batteries. The cheapest ones. Okay.
Build your own.
And people claim, I've just heard last night that someone said that they can't understand why inverters are so expensive because they aren't that complicated. But I'm not an electrical engineer, and they seem pretty complicated to me. I'm just happy if I can make them work. Anyway, an inverter basically converts DC power to AC power. That's by definition the job of an inverter. You're all familiar with that, what I'm talking about there. Solar panels make DC power. Batteries have DC power. And if you want to use that power in a more conventional way, you'll want AC power. This room is powered by AC. And most of the things in your home are going to be AC, at least when you plug them in. Now, surprisingly, many of your things in your home are probably DC. Your television, your computer, your audio equipment is probably DC, but the conversion is taking place, reverse conversion is taking place. It takes AC in and puts DC to run the device. And so when you have an inverter, or you have a need for an inverter, you need to define what you want that inverter to do. That could be nearly anything. People in their home are going to want to run lights, motors, audio equipment, and all these devices have different needs, and then you need to figure out the inverter that's going to best satisfy your need without, going to excess expense or anything that will not meet that need. I really struggle with trying to cover both topics, the grid tie without batteries and the battery inverters. But there's a lot of generic information, okay? Inverters normally come with two major characteristics that you have to think about right off. There's size. Inverters come in a lot of different sizes. And the size, I'm talking about how many watts of power can it provide on a continuous basis. So inverters are rated for their continuous output. They will typically surge to a higher output. So if you have a 1,000-watt inverter, it very likely could surge to 2,000 watts. And why surge is important if you're trying to run a motor. A motor also has a continuous power requirement, but it will surge anywhere from 2 to 3 to 5 times that continuous requirement when it starts up. And so you want to have an inverter that will meet that need, that will have the capacity to start that motor and also let it run continuously while it's doing its work. So you look at an inverter's power rating. The next thing that you have to think about is the quality of the inverter's output. The terms that are most commonly used are sine wave, pure sine wave, or modified sine wave. When we talk about sine wave with electricity, a sine wave is something that looks like this, roughly. That is, the electricity goes from 160 volts to 0 volts, back to 0, negative 160, back to 0. That's a typical sine wave. The voltage will flow like that, and that nice smooth flow makes equipment run better, more efficient. A motor will run more efficient if it has a nice pure sine wave of the flow of the voltage from that device. Now, you normally hear of 120 volts. That's what we talk about. You have 120 volt, and the gentleman said earlier, single phase. Okay, I'm talking about a single phase, 120 volts. And the reason that it's called 120 volts is that that's RMS, root mean squared. It's the 45-degree angle where it intercepts the sine wave curve. They call that 120. A lot of times you'll hear 240. 240 is actually two single phases that are inversed from each other. That's a 240 sine wave. It goes in both directions, meets at 0, and goes the other way. And so you will have the difference here from that 120 to that 120 is 240 volts. And that's what you'll often hear about, single phase 120, single phase 240. Okay, the inverter will do that. If you have a sine wave inverter, it will make an output very similar to this type of curve. Now, if you have a modified sine wave, a modified sine wave tries to copy a sine wave, and it's basically a less expensive way to do this job, but it's not really a sine wave, and some of your equipment won't like it as well. It still works. There's some very good quality modified sine inverters, but instead of having that nice smooth curve, they will do it by pulse width modulation. And so what they do is they turn it on at maybe, it might not even be 160, it might actually be 120, something like that. They will turn it on for a fraction of a second, turn it off, turn it on for a little longer fraction of a second, turn it off. And so they do that in pulses. And so the total area underneath these pulses while it's turned on will be approximately the same amount of area underneath a true sine wave. And so you can fool most equipment into working properly with a modified sine wave inverter. You will run into trouble, you know, if it's a good modified sine, it'll run nearly anything. If it's a really cheap one, you'll have trouble. What people have had trouble with in the past, the one that comes to mind, I fried a cordless drill's battery charger by plugging it into a modified sine wave inverter, and the charger just didn't like it at all, and it melted the battery, which was kind of an expensive way to learn to be careful with modified sine inverters. But many of them will work. You just have to be aware of that, what you're getting. So, repeating what I just said, sine wave is better. Motors will run quieter. They'll run more efficient. A motor will probably run 10 to 20% more efficient with a sine wave than a modified sine wave, and you'll get a little bit of noise. You know, my hearing's not that great, so I don't hear it that often, but I have customers who are more sensitive that go, that doesn't sound right. And they'll call me up and say, there's something wrong here. And I'll say, no, you have a modified sine inverter, and that's what it's going to do. Input voltage is another characteristic that you will be thinking about. And a lot of this, I originally made this presentation for the battery-based inverters, and now I've kind of added some of the, you know, not battery-based inverter information, so I'm going to be jumping back and forth. Input voltage. If it's a battery-based inverter, you will be usually working with denominations of 12 volts. 12, 24, and 48 are the common input voltages. 12 volts, I think, is a device of the past unless you're doing something small. You know, like you want to plug it into your car, okay, you got 12 volts, great. Get a 12-volt input inverter. If you're doing something like a cabin or a home, 12 volts really isn't the way to go anymore. The 12-volt amperage is so great if you want to get up to any level of power that you run into really expensive and large wire. Wire size, when you're talking about wire size, and I might have a slide on this too, but anyway, you worry about the voltage drop. And that's going to be equal to the resistance of the wire times the amps, how many amps you're running down that wire. And so when you're choosing wire and you're sizing wire, if you have a lot of amps, wire size is built around the number of amps on the wire, and power is, watts equals volts times amps. Little basic electricity. So if you can up your voltage, if the voltage goes up and the amps come down, you can use smaller wire. And that is, it's actually every time you double the voltage, you cut your wire size by a factor of 4. So if you have a choice between 12 volts and 48 volts, your wire size can be 1/16 the size to move the same amount of power. So just a basic fact that if you can choose your voltage, you really don't want 12. 24 is good and common, and if you're getting into a big application, 48 volts is probably the way you want to go. Let's talk about grid tie inverters. That's another whole story altogether, but the same principle applies. The grid tie inverters are the inverters that take solar energy, send it to the inverter makes the output identical to the power company. So that's it. It makes for a very simple system in many ways. Solar, inverter, grid tie. Those inverters are almost all in the range of 150 to about 400 volts of DC input. Really high voltage, you can use some pretty small wire. Output voltage. The grid tie inverters are typically 240 volts AC output. When these inverters first go into operation, they are going to synchronize to the power company. And the power companies are very fussy about this. They're becoming more familiar with it because they have to, and it's growing. It's more common in Europe and California, but it's happening more in Iowa now too. And they have a concern. They go, I don't want you electrocuting or hurting our repairmen. If the grid goes down, I want to make sure that you are not sending power out there. That concern is not really valid because the inverter takes care of that. The inverter will look at the power company. Before it comes on, it looks at the power company's electricity coming in. And I consider it kind of like riding a wave with a surfer. The electric company is looking at that sine wave coming in from the power company. And that sine wave is making that ride 60 times a second. You hear the term hertz, 60 hertz. That's what the power company delivers to your home. That means that 60 times per second, it's making that sine wave, that 140 or 240 or 120 sine wave, 60 times a second. The inverter will sit there and look at that sine wave and synchronize to it. And when it's sure that it has it all synchronized, then it will turn on, take the solar power, and start sending it out exactly as the power company is coming in. It has to match the voltage, and it has to match the frequency within a very narrow band, like 5 or 10%. If it doesn't have that voltage, and the power company's voltage has to be within that 5 or 10% range of the inverter. It has that, then it'll start sending power out. And it checks that many times a second during its entire operation. So if the power company goes out of that range for whatever reason, shuts down or just has some other anomaly on their lines, as soon as it goes out of that range, the inverter shuts down instantly. And if you understand it then, the inverter requires that signal to make power. If it doesn't have it, it goes down. So if the power company shuts down, the inverter has no reason or capability of sending power out. This is a standard, if you've heard of the UL Underwriters Laboratory. Okay, Underwriters Laboratory has a standard that inverters must comply with that proves that they meet the